we are very glad that from Indian Institute of Astrophysics in Bengaluru. Moushumi has a very strong connection with the presidency, both as a student and as a mentor. So Moushumi was a student in the Israel Presidency College. I was just showing her a picture of her in the BSc lab, which was published in the Reunion magazine. So she was a student here from 1983 to 86, and then went to Calcutta University Science College for masters, and then he joined the JAP program and a PhD student at IISc, worked with Professor Chanda Jog. And then after her PhD, she was a postdoc at RRI, then a research associate at University of Maryland, and then again came back and was a postdoc for some time, and then became a faculty member at Indian Institute of Astrophysics. And Professor Dash's expertise is in galaxies, so various properties of galaxies, galaxy evolution, star formation inside galaxy, bar formation, and so on. The connection from the mentor side is one of our BSc MSc students, Shairi Ansar, did her PhD with Moushumi, and she's a postdoc at the Flatiron Institute now.
She's in Durham.
She's in Durham.
Yeah,
Durham. Right.
Yeah.
Right. And also, I think Deepsha here has done some work, and now two other students of presidency are working as postdocs with Moushumi. One is Abhinanda, who many of you, I think most of you know, and also Prerana Vishwas, who most of you don't know because she left much earlier. But she was also they're all the same batch. Somehow that batch has great connection with
me.
Yeah. So both students from here went and worked with Moushumi, and Moushumi earlier in her life was a student here, and so today we are very glad to have her, and we get to hear from her.
Okay, thank you. Okay, thank you. First of all, I just want to thank you both for inviting me here. It's so nice to come here. Not a lot has changed. No, this part has changed. This part is all new. But the vibe is the same. Graffiti is similar. So the whole attitude, everything is the same. So it's very nice to be here. So thanks a lot. And secondly, before I start, so since it's quite informal, I think you can ask questions, right? Yeah, sure. Ask me questions, whatever you think of while I'm talking. So today what I'm going to talk about is some work I've been doing for several years, more than 10 years now with students. And how it started out was when I was very bored one night observing, I was looking through spectra, SDSS spectra, and I found some spectra had double peak lines. And so it was split. So I saw H alpha lines which were split. And I thought SDSS had an error. I went to my friend. I said that SDSS has made a mistake. I have found a few of them. And she told me those are double peaked spectral emission lines. And two peaks, if you have two peaks, it could mean that there are two nuclei. Okay. And I think most of you know what is the AGN, active galactic. Yeah, okay. So if you have an AGN and it's giving out emission lines, and if there are two nuclei, you may see two emission lines. Okay, so that's where it all started, from examining spectra in the lines. From there, I've gone to looking for dual AGN, two AGN in galaxies. And after that, like 7-8 years ago, when there was the detection of gravitational waves, I became more interested because when you have dual AGN, it means two supermassive black holes. And if they are coming closer and closer, their in spiral will lead to the emission of gravitational waves. So looking from galaxy mergers to dual AGN, you can find out the sources of gravitational waves. Okay, so that's the big goal in that talk. Now, there are many people. Abhinanda is here. She's a big contributor, as well as Prerana over here. Shairi did some other work with me. That work was more about simulations, the dark matter halos. So I'm not talking much about simulations here. I'm just talking about observational studies of merging galaxies mergers. Okay, so this is the brief outline of my talk. Maybe I don't need to do what is galaxies here. I probably, yeah, I think I can skip that part. But I will talk about AGN, the model of active galactic nuclei, even though many of you may know. And then I'll talk about the different type of galaxy mergers, dual binary AGN as the progenitors of merging supermassive black holes. And then I will, towards the end, I will talk about a couple of projects that I'm doing with Prerna, with Avinanda, and I've done with some other students and interns. So this is the general thing. So this one I will, yeah, what is elliptical? And I think you all know since classes have been done. Okay, one thing I will just like to mention about the elliptical and spiral galaxies, because we are talking about galaxy mergers. Galaxies, unlike stars, are collisional systems. So if you have big galaxy clusters, the density of galaxies towards the center of the cluster is very significant, and so galaxies will pass each other, affect each other gravitationally, and they will merge. So one thing is that the two types of galaxies are different. There are the disk galaxies or spiral galaxies. You have the elliptical galaxies. Disk galaxies are rotationally supported, whereas the elliptical galaxies are supported by random motion of the stars. So this makes, when you see galaxy mergers, when you're having a merger of example, a disk galaxy and elliptical galaxy, the outcome can be different depending upon, of course, the nature of the galaxy, but also on the masses of the galaxies and the orientation of the galaxies, how they're coming, how the orbit is coming close. So I just wanted to show this because of that. Now we all know that the centers of galaxies contain supermassive black holes. So supermassive means 10 to the power 6 solar mass. And some of them, if we do not see the supermassive black hole, it might have been kicked out. So we all know that. Now this is the general picture of a accretion onto a supermassive black hole. Now one thing that we have to remember is that you cannot see a black hole unless it's accreting. Okay, so the black holes that we see nearby, like the one in our galaxy center, we see it because it's very close, or M87 is very close. But in general, for distant galaxies at higher redshifts, the only way you can see them is when they are accreting, because when they accrete mass, they will give out luminosity, they'll give out radiation. So the radiation that in observations that we look at is some radiation coming from the accretion disk around the black hole. That radiation can be UV photons. Those UV photons later on, when they see these BLR clouds, compact clouds, then they will get dispersed. They'll get, the radiation will move from here to here and here and finally come out. Some of the UV photons will finally come out and reach the narrow line regions. Now, these photons that come out, either as UV or as H alpha photons, they will be telling us something about the AGN. So, for example, if we see an H alpha line that is split, then that H alpha line split could mean that there are two supermassive black holes here. So that's why you're getting two lines. It could also mean that the split, observing spectral split that I put here, is detecting outflows. Okay, so a split in the line emission can be H alpha emission, it can be O3 emission, it can be H beta or H gamma. It can mean, number one, that there are two AGN, but it can also mean that there are outflows. And if the two components of the line are equal in strength, it possibly indicates that's a rotating disk. So all of this starts from our AGN unification model that is shown here. Now, because of the accretion onto the black hole, there is a lot of luminosity given out, and that luminosity is what we detect. And that luminosity, which you can say here and here, usually becomes brighter and brighter as the galaxies come closer and closer. Now, I've shown you here some pictures of galaxies merging. You can see that, as they are disturbed, if they have disk, then they will be tidally affected. They can come close like this in the plane. They can come close at an orbital angle. So you may have many things happening. But one thing is clear, that if you have two galaxies coming closer, the nucleus becomes brighter. And that's because when the galaxies are quiescent, then the gas clouds are moving in nice circular orbits, or the stars have their nice orbits. But when there is a gravitational perturbation, those orbits are affected. There is cloud collision, orbits are affected, clouds collide. When clouds collide, gas is shocked. When gas is shocked, it goes to high temperature, then cools, and after gas is cooled, it fragments. Gravitational instabilities make the clouds fragmented. Now, fragmented clouds will start now collapsing. They will collapse to form stars. So the first thing that you will probably see when galaxies are merging, if even one of the galaxies has gas, is you will see star formation from the process that I just now mentioned. Now, even if you do not have gas in some of the galaxies, and those mergers are called dry mergers, then the orbits of the stars are affected, and there could be some stars that will fall to the nucleus of the galaxy, leading to tidal disruption events. That also gives out luminosity. So in general, when galaxies are merging, we will see the nuclei become bright. Now, there is a small classification, not very strong, but in general, when galaxies are merging, we can classify them as wet mergers and dry mergers, depending on whether even one of the galaxies has gas. So a wet merger is a merger in which one galaxy at least has gas, so that there is star formation. Okay, so that's why a lot of the mergers seem very bright. When the two galaxies have similar mass ratios, 1:1, 1:2 or 3, we call them as major mergers. But when one galaxy is much smaller than the other galaxy, it's called a minor merger. So wet and dry mergers, and minor mergers, major mergers. Now, the classification is slightly important, because if you have a major merger of, say, two disk galaxies, it will always lead to the formation of an elliptical galaxies. So that's why very often you will find that in some elliptical galaxies, you see two components. And some people have said that especially these elliptical galaxies can have many black holes, which are called wandering black holes, because there could have been many mergers in the past. So these are just some of the classifications. Now, as I mentioned, as the galaxies come closer and closer, you'll find their nuclei becoming bright. This is in X-ray, and you can see here is a close-up here, two nuclei, but it's very difficult to catch them. You need good resolution to be able to detect the two bright nuclei in the centers of merging galaxies. But this kind of what I just mentioned, galaxy mergers leading to star formation because of the gas, cloud collisions, and then the star formation can also lead to starburst and AGN activity in the nuclei. This sequence is now quite well established from observations of galaxies. Now, after this happens, after the nuclear activity is triggered, there often is the formation of a more massive galaxy. And if both the galaxies are disk galaxies, then it will be an elliptical galaxy. So this is one way of forming an elliptical galaxy with an active galactic nucleus. And that, if it gives out radio jets, becomes a radio galaxy. So this kind of a sequence is something that we've been trying to look at in radio with Sumana. And if I get time, I'll talk about it, but it's not really part of this talk. So I just wanted to show this image here. Have some of you seen this image? It's an image of a very famous group. Yes, the quintet, right. So in the quintet, I wanted to show this because it shows you how important galaxy mergers are for not just making the nuclei bright, but also pulling out the stellar debris. So when stellar debris, tidal tails are all pulled out like this, it leads to a lot of star formation and a change in the morphology of the galaxies. So basically what is happening is as the galaxies come closer and closer, their kinetic energy that is associated with their motion towards each other, that gets converted into their internal energy. So this is very simple to understand from classical mechanics. So that energy is becoming converted to their velocity, stellar velocity dispersion. So this is why when you have many of these mergers, then the result becomes an elliptical galaxy because the rotational motion gets destroyed. So there are many options for having this merger. There can be, as I mentioned here, you can have elliptical mergers, you can have elliptical disk mergers, or you can have just simple disk galaxy mergers. But the final result, especially of the disk, depends upon what is the mass ratio and what is the gas fraction in these galaxies.
Mostly, you mean that is half MCM VCM square, right? The center of mass.
Oh, okay. Half? Yeah. Sorry, yeah.
No,
I missed that. Half.
That's
Yeah. BCM I missed. Sorry. Yeah. Yes. Yes. Because we studied this in simulations, and if you have another galaxy going by, there's so much energy pumped into the system that it's very difficult for it to go back to normal later on. So I'm not talking about simulations here, but since he mentioned that Shairi was my student, you can guess I do simulations. In fact, I started out doing theory. Galaxy mergers in simulations has been studied now for many years, for decades. And one of the first earliest ones which really showed interesting results, Barnes and Hernquist, 91 and 96, showed that when you have galaxy mergers, it is not just, that there is a mass ratio or that there is gas present. It also depends upon the orientation. So you could have polar orientation, you could have an angle of inclination. And in us, we also did simulations. Ankit, who was my previous PhD student, we also found that it makes a very large difference. Of course, when you have them both in the same plane, that's when you get the most gravitational effect and the most result on the galaxies. Now, these kind of simulations now have become very sophisticated. Barnes and Hernquist had only stars, but now with TNG50 or Fire, Eagle, many simulations are there where you have gas as well. And that's very important because when you have two galaxies merging close to one another, it's the gas that really responds because there are cloud collisions and star formation. And that's where you can really see the effect of the merger and how you can actually see that the nuclei come closer, spiral inwards to each other. This you can see in some simulations. Of course, not all of them have the resolution. Some of the best simulations have resolution of only 1 kiloparsec. And 1 kiloparsec is not enough really to see. So I'm not going into this part, but simulations are wonderful to study galaxy mergers. Another thing which I haven't mentioned is galaxies, it's not just the orientation, but it can be the prograde, retrograde approach of the galaxies. So if a galaxy is rotating like this inside, and another galaxy comes with the same sense of rotation, a prograde rotation, then there is a lot more effect than if it is going against the rotation of the galaxy. So these are just some of the effects which are very wonderfully studied with simulation. So I have this. Okay, now that I've told you a little bit about galaxy mergers, interactions, any questions? No? Okay. So stop me if I'm going too fast. Okay. So now that you know that the nuclei start to get bright as the galaxies merge together. And you know, nuclei bright or galaxies become bright because of two things. One is star formation, and the other is accretion onto the black hole, okay, which is AGN activity. So as the galaxies come close, you can have nuclei of different types. You can have star forming nuclei, SF. Yeah, you can have different pairs. You can have star forming pairs, you can have AGN pairs, you can have mixed pairs. Now, this is important to understand because if you are seeing an AGN pair, it will become a dual AGN as we interpret it. But it is also a kind of a signal that there are two accreting supermassive black holes here. Okay, it's a confirmation. Now, there is a certain classification. What do we call a dual AGN? A dual AGN is when the AGN are separated by more than 100 parsecs. From 100 parsec to maybe 30, 40 kiloparsecs. So that's a dual. Now, a binary is very close. A binary AGN is a system where the two AGN are separated by less than 100 parsecs. And so those 100 parsec or binary AGN are systems where the supermassive black holes are very, very close and spiraling around each other. Now, that's important because when the supermassive black holes are so close, then they can affect each other. Their outflows will affect each other. As the gas accrete, the outflows. Then also their motion can also, their spins, these can also start affecting each other. So here I've given some images of dual AGN, well-known dual AGN. Here is an SDSS source. This one is very famous, 3C75. And this is also famous Markarian 739. Now this one, which is 3C75, you can see here, there are two compact nuclei and there are jets. Okay, so it's like you have two systems with jets coming close to one another. And jets are made up of thin streams of plasma, hot plasma going out. So they will be affected as the nuclei come closer to one another. They may precess also. Now, on the right-hand side, this is a system where there has been a merger, and you can see that there are these spiral arms, and the two nuclei are embedded in a disk. So this is really what is a kind of the poster picture of a dual AGN system. You will have two bright nuclei embedded in one single envelope. Okay. So our aim was to detect such pairs of systems, dual AGN. And the reason was that, first of all, they're very interesting sources because they are two supermassive black holes accreting and coming close to one another, but also because they affect their environment. When you have two AGN coming close to one another, both the AGN will have outflows. Both the AGN will also be affecting their environment through short outflows or very large outflows in jets. So there will be AGN feedback. And so that AGN feedback, when there are two of them, can be much more powerful than when you have one of them. So the galaxy evolution can be much more different. And so it's important even for early epochs of understanding early epochs of the galaxy, and also for enriching the circumgalactic medium. Okay, so which we know is enriched from very early epochs. So how does that happen? This is also an important question. And the last, I said AGN feedback, CGM. Okay, and of course, finally, supermassive black hole binaries. Now we know since last nearly 10 years, we know that there is gravitational waves. We have detected them. People have detected them. There are gravitational waves coming from the merger of neutron stars, neutron star black holes. But these are all systems which are in our galaxy or maybe a nearby galaxy. And they give out enormous amount of energy and gravitational waves. But there is also now what is called the nanohertz background, gravitational wave background. And that background at very low frequency is thought to come from objects which are supermassive black holes going around each other in spiraling, and other massive sources, but this is a major one. So if we can detect more and more supermassive black hole binaries, we will be able to understand more and more about the gravitational wave emission of gravitational wave, their origin. So that's another big, for me also especially, that was a big important reason for studying dual AGN. Now, dual AGN, I've just talked about two AGN, but AGN can cluster because I showed you in the first few slides, there's a Stephen's quintet, which is a small group. So AGN, if all of them are having supermassive black holes, we can also have the clustering of black holes in our universe, which will also add to all the effects, CGM, AGN feedback, which I have mentioned here. Okay. And so this is just a cartoon. If you see it later, you will understand what I mean by a sequence. There's the galaxy merger happening here in the beginning. The nuclei come within a single envelope here. Then finally, from the dual system, a binary forms. And if the black holes here start in spiraling, we will finally get continuous gravitational wave emission. So that's really the kind of a
Yes.
huh? Hmm.
Gravitational waves from supermassive black
Ah.
hole mergers. I think these gravitational waves that you spoke in the
Hmm.
nanohertz,
Ah.
they are like even much closer than what we call the dual AGN.
Yes, of course, yeah. So a dual AGN is like the starting point.
Binary.
Yeah, so
Yeah.
even much closer than the binary.
Even much closer than the binaries. So I think I have a slide here. This one, the slide. So a binary AGN, which is a signature of two supermassive black holes very close, is very rare. And now, as far as I know, there are only three of them. But I may be, yeah. One is the very famous OJ 247. 287, yeah. So this quasar has been observed for nearly 100 years. No, more than 100 years, no? Yeah. 130 years, imagine. So there is a variability in the light curve of this quasar, yes. And so I think many of you must know that. It's thought to be due to a binary black hole system. But this one is a minor, I think. Here, this is considered to be a minor. 10 to the power, no, this is 10 to the power 8. And this may be, I think, a little 18.
These are both supermassive.
Both are supermassive, yeah. 100, huh? Okay. So the other one, which I think is very interesting, is the one in 4C plus 37.11, where there are the two nuclei. These are two AGN. You can see them as compact cores, and one of them has radiojets. So that's a very well-studied system now. So it's quite rare. And this one is detected by Preeti Kharb, who's at NCRA, where she detected using this radio astronomy technique called VLBI, where you can see milliarc seconds. You can detect, you can do a spatial imaging in radio at milliarc seconds. So these were separated by around less than a parsec, actually. So we also did, because, this source had never been looked at in X-ray. We looked at 4C 37.11 in X-ray using Chandra archival data. So what we found is we detected a FeK alpha line. Now, we thought this was interesting because it shows you that some of these sources, the binary AGN, if we have in future better and better X-ray instruments, we may be able to detect two FeK alpha lines. So for one system, it's already there in GC 6240. Do you know? Okay, 6240. But so the very important thing about this FeK alpha line is it's coming from the inner part of the accretion disk. So if it's from the inner part of the accretion disk, it will be affected by the spin of the black hole. So one of the ways to understand more about the spin of the black hole in merging systems would be to study the FeK alpha line in these kind of merging binary black hole systems. So that's why we did this, and we found only one line, but we thought it was important to put the word out that this is an important measurement. Okay, so this I will now go back in history. So how we started studying these dual AGN system. This was the first one we studied. It has a nice double peaked emission line, which you can see over here. Then we looked at it in radio, but we found it had coronal. We interpreted this single source as emission, radio emission coming from a disk. So it's a disk, and one of the reasons why we thought it must be a disk is you see the emission lines here, the double peaks are nearly the same. So it could be a rotating disk around a central black hole, and we are seeing a double peak because of the approaching and the receding emission. Okay, so we did, over several last decade, we've been studying many of these emission line galaxies because they're the ones that have strong emission lines coming from the nucleus. And one thing we found is that most of these double peaked emission lines are not a signature of 2AGN. So that was disappointing, but that was something, a result I think that was coming in the literature. In some cases, because we were studying these double peaked emission lines in radio, we found interesting sources, and this is one of them, which was found by Ruby. What we found is these two compact sources here, they are not 2AGN. Actually, what they are is hotspots. So there is an AGN in the center, which is giving out sub-kiloparsec outflows, and those outflows finally have hotspots. Okay, but what is interesting is that there is a curvature in the jet. Okay, so the curvature in the jet can be due to some gravitational perturbation, something that making the black hole precess. And one of the things that can make a black hole precess is a companion. So we think that in this source, there is a black hole here, supermassive black hole here, but around it is another companion. And that companion is small, and Ruby actually modeled all this precession. And because it is small, it makes the black hole spin. And when the black hole spins, then its jet also precesses. Okay? So this kind of S-shaped jet precession actually is studied widely in the literature. There are the so-called, what is it called, those S-shaped sources. Yeah.
Wide angle tails.
They are also, those I think due to RAM pressure. Huh? Yeah. But the X-shaped sources are like this, but much larger scale. S-shaped, yeah. Hmm.
Not the proposal was that there must be a companion, maybe smaller mass companion, which is actually making the black hole precess and its jet is precessing.
Yes.
Is it possible that there could be, I mean, is it the only way we can have this S-shaped
no.
precession, or there can, because you know,
Yeah.
Good. Two questions. Second is, are there any possible further studies in maybe other wavelengths or other kinds of studies that can definitely tell us yes?
Yeah. So this I think was at in that 2 to 10 gigahertz band. We wanted further higher, if we did further higher frequency observations, I think it would tell us more. But your question, that can be another explanation. It could be that the black hole spin flipped, because you see it's in one direction and then here it is in another direction, S or Z shape, right? So it may not be precessing, it may have been just flipped by some companion. The black hole spin.
Expect such kind of jet.
You will see, you will see some change, but that change may not be a slow change. Right now, see the resolution, na? So Chetna, I don't think you can tell whether this is a continuous structure or whether this is like a Z-like structure. VLBI, not VLBI. This is with high resolution VLA. Yeah, I think our problem was that it didn't have enough emission to do the VLBI, and then Ruby finished her thesis also.
And also, I guess the angle of the jets to the line of sight will also make, this whatever is, this is the apparent projected change that we are seeing. But the actual, actual bend is not that. It's something else.
Yeah.
But how much that is different, that depends on the
viewing angle. Yeah. So what she did, this was several years ago, but I remember there's another source called SS433. Yeah, SS433 binary, Telema's binary. And that has some very good modeling. It has two processing and the jet, and it's not even modeling, it's observations. Right? There are some very, yes.
So then you can compare that.
Yeah, so we compared that with this. In fact, I remember she used to show that video of SS433 in her talks.
So, by the way, just take a step back. So, you were looking at SDSS spectrum, and if you see a hint of a
double peak,
double split line, then you are trying to observe it in radio because it will give you better spatial resolution, and you are trying to understand.
Exactly, yes.
Well, peak one will have definitely radio emission.
No, it's not. It's a luck. Yeah. In fact, that brings me to this. This actually shows our result. We did 20 sources. See, we had to choose not only double peak, we had to choose double peak which had radio emission. Otherwise, you can't ask for radio time. So out of 20 sources, we found only 3 appeared to be good candidates for dual AGN, okay, based upon their radio emission, spectral index in radio. Okay, so, and I think finally we found only one of them was a confirmed dual AGN, because you have to also take their spectral lines and check that they are AGN emission lines using the BPT plot. So that made us the conclusion that the double peaked emission lines are not a very good method to find dual AGN. So what we thought would be better to detect dual AGN was to actually use dual nuclei galaxies. So we thought that instead of just looking at the spectra, we should actually see 2 bulges, 2 nuclei coming close. And then we go and check whether the nuclei have AGN or not. So this happened a couple of years ago. I changed the tactic. Okay, yeah. So because one of my students was working using Astrosat UVIT data, we looked at some merging galaxies with UVIT, and then we also followed it up with MUSE data, because UV comes from star formation or emission from the accretion disk around the AGN. So it will tell you whether there is a bright nucleus, whether there is star formation and tidal tails around the merger. But it will not confirm that there is an AGN. For that, you need spectral lines and you need the velocity also. So this is one thing that we realized very early on, is that when you see 2 galaxies and they're merging, unless you know their velocity, systemic velocity, you can't tell whether one galaxy is foreground and one galaxy is background. In fact, Jyoti had a paper on this, because one of our sources in our survey, UV survey of merging galaxies, it had a very peculiar tidal tail. And we saw it in UV, and in UV the peculiarity became even more. Okay, so then what we did is we were lucky enough to get some spectral lines from, I'm not sure what, maybe only SDSS, and we found that one was foreground and one was background. So it wasn't a dual system, or it wasn't a tidally disturbed system. It was 2 galaxies. One was in the foreground and one was in the background. So this is just an example. She looked at this pair, NGC 773334, And what she found is that there is a third nucleus in the tidal arm of 7733. And that third nucleus, because we had Muse data, we could determine that it was a Seaford nucleus. So this was a triple AGN system, and it was the only second that was known. The first was in X-ray, and hers was the second one. This is also another UV study I thought I'd show you, where you can see the UV emission. This is a UV plot. UV is very bright in the center of the galaxy. And you can see UV emission here, which is associated with this number 4 and number 3. We also have corresponding radio emission, so radio maps of this source. And what we find is that these two blobs correspond to two kind of outflows. So it's like jet interaction, jet cloud interaction. So there might be some clouds, some gas, and there is jet cloud interaction leading to star formation. So there we found these two. But this also has a very nice spiral structure. You can see spiral arms here, you can see spiral arm here, and one at the back over there. So it was a very interesting system to study, dual AGN.
Scale length of these systems?
So their nuclei are separated by 11 kiloparsec. Yeah. So so this separation is about 11. So it classifies as a dual AGN, not as a binary. Okay. So that's why I'll move on now to using optical imaging to find dual AGN. How long do I have? I can keep going on for a long time. So you have to tell me to stop.
10 minutes.
Oh, okay, it's 10 minutes. So I'll move very fast. Okay. Okay, 15, huh? Okay. Okay, so this is a project which was done by an intern who later on went to do computer science. So he used, what he did was he took 1,000,000 galaxies from SDSS, and downloading 1,000,000 galaxies was a lot of work. And he used Google Colab, which I had never heard of. This was several years ago. And he downloaded all those galaxies. And SDSS gives you 5 wavelengths, U, G, R, I, Z. And what he did was he made their little images using DS9 and made JPEG. And then he looked for nuclei, multiple nuclei. Now with image processing, you can do something what is called hill climbing. So you can go and see the intensity of emission and find peaks in the image. And those peaks, if they are more than one, then he started filtering it. So he used this image processing method. It's not ML actually. It's not any AI type method. It's just simple image processing to find systems which have 2 nuclei. So basically mergers. So I've listed some of the steps he did, but it was really all his work. I'm not too familiar. But he got, you should see his paper. I don't have the numbers here, but he started with 1,000,000. And then with 1,000,000, he went down to 100,000, where there were suspected 2 nuclei. Now from 100,000, he went down to, I think, 40,000, because he checked their redshift. You can't have, foreground, background. They all had redshifts. So he found whether they are both at the same redshift. So that also, I think, went down a few thousand more. Then the last check that he did was that the 2 nuclei should be in all the wave bands. So you should have them in U, G, R, I. I think Z band wasn't very great. So doing this, he found something like 1,100 or 1,000 nuclei, which were kind of definitely nuclei. And then we did a visual inspection, and we also put them on the BPT plot. Now the BPT plot is, I think they might all know BPT plot. Okay, so the BPT plot it's an empirical plot which tells you whether the emission can be due to Seaford AGN or weaker AGN, a liner, which is over here, or whether the emission that you see from spectral lines can be due to star formation. There is also a region here which is called composite, which is due to nuclei or galaxies which are having a mixture of AGN and star-forming emission. Okay, so this is all coming from the emission lines, spectral emission lines. So it was very important to have both imaging, redshift, and spectral lines from the nuclei. So with this method, we were able to find 159 dual AGN and several star-forming pairs and star-forming AGN pairs. Now, the interesting thing when we put them on the color magnitude plot of galaxies is that the dual AGN all mostly lie on the red cloud, which means dual AGN are preferentially found in evolved galaxies. So I think this was really the most important result that we got. But we also, and this is just an image of them, just to show you what they looked like. But what we really needed to see was, after that, we needed to investigate this sample. So this sample, as I mentioned, was 159 dual AGN, but there were also 682. Actually, 682 was the total number of nuclei pairs, out of which 159 was dual AGN. Now, there were two things which we really wanted to do with this. The first is we wanted to find out what are the types of galaxies that we expect to find dual AGN. Because if dual AGN are finally going to come closer and closer and become binary AGN, then when we see binary AGN or we see sources that give out emission gravitational waves, we can say, okay, it's an elliptical galaxy, so it's more likely to be due to a binary AGN or a binary supermassive black hole. So finding the sources of binaries for gravitational waves, that was one of the aims. The other one is to see the black hole masses. Okay, and that is what Prerna has done, and I'll quickly show you. And the third was to find out what are the type of galaxies, what kind of galaxies are we most likely to find dual AGN. And let me just quickly show you his results, Nehal's results. So this is the Sersic index. The Sersic index is an indicator of what kind of bulge, okay, that the nucleus resides into. And you can see most of the nuclei lie in this orange region. And the orange region signifies classical bulges. Now, classical bulges can be the strong classical bulges in disk galaxies, or they can be elliptical galaxies themselves. So what this result, his main result was that,
Red to so the pair, signify the pair or what? The red and blue colors?
Okay, yeah. The blue is a pseudobulge. Okay, pseudobulge, yeah, because you have very few of them. So a pseudobulge is a kind of a boxy bulge, not a classical bulge. But the red ones here, they are either classical bulges in disk galaxies or they are elliptical galaxies. So you can see most of them lie in this. Okay, so I think an easier way to see is this pie chart here. In the pie chart, you can see that it's mostly major mergers where the dual AGN lie. It's mostly elliptical, disk elliptical or elliptical galaxies. So the dual AGN are mainly found in host galaxies which are elliptical or disk elliptical in morphology. Now I'll quickly go through Prerna's work. What Prerna did was she took all these 682 pairs. Now these 682 pairs have star-forming galaxy nuclei pairs and they have dual AGN. And she did a lot of work using PPXF to look at the spectra. Now from galaxy spectra, what you can do is you can find out the black hole mass. Okay, from you take the spectral lines, and from the spectral lines and their broadening, you can put an estimate of the black hole mass. You can also put an estimate of the accretion rate, the Eddington accretion rate. And so I'll just show this plot from her work, which is we will submit shortly. If you see this black line, the black dashed line, it's at the lower part. And all the red points here lie above the black line. Now that signifies that the dual AGN, the black hole masses of the dual AGN is higher than those of the regular galaxies we see in the low redshift. Okay, which means that as the galaxies are merging and coming close to another, their black hole masses are growing. So the growth of black holes is not just due to the merger of two black holes, it is also due to the merging process. So I thought,
that's the N star engaged for what? For local galaxies? Or
yeah, actually, this is by Rains and voluntary. Do you know this work?
That's must be some theoretical prediction.
No, that actually I think they use the spectra. They use the spectra. But this is one problem. We have to now just revise our paper. We don't exactly know how they found the black hole masses and how they chose their sample. Prerna just took their result because they have, I think, several thousand, 100,000.
Something. That must be controlled.
Yes, yes. The redshift distribution is very similar to ours. Yes, it's less than 0.1.
These are like
0.3. Huh? Yeah. So that is one thing that we have to check out. They have just taken a general population. They haven't taken any specific type. So, but this is something we are doing a little more investigation. Now the blue ones, they have a lot more scatter. They are the star-forming ones. So it's really the dual AGN and the AGN star-forming pairs which are lying very systematically above the dashed line. Okay, so this is metallicity. I'll go on since we're running a bit late. Okay, so this is something we have just started. It's so the black holes are coming closer and closer. So we wanted to see something further. Okay, when they come close and they are bulges, like the black holes are embedded in these stellar bulges, as they come closer and closer, do they become embedded in a common disk? Or do they have their own separate disk for a long time? The other question we wanted to ask is, as they come closer, do their bulges get tidally distorted? So to answer some of these questions, we've been looking at this nearby, this is the nearest dual AGN, NGC 6240. And 6240 here has two AGN here. And let me show you the JWST image. This is JWST NIRSPEC image, collapsed image of the two nuclei in NGC 6240. Now you can see here that when a very high intensity, the bulges seem more or less like classical bulges. But as you go further and further out, there is some distortion. And in fact, over here, it looks like a tidal bridge. So this may represent one stage in the evolution of a dual binary system.
Is it NIRCam or NIRSPEC?
NIRSPEC, actually. NIRCam is not there. It's very sad. So we had to take the NIRSPEC, collapse it, and then there is some PSF you can use to kind of convert it into a NIRCam image. So let me show you.
You have spectral information.
Yes, we have spectra, because I want to see also in this bridge what are the stars. So this is definitely like a tidal bridge happening, evolving between the, yeah. Okay, so yeah, I won't go into that. This is Abhinanda's work. It is also work in progress. Now, Abhinanda is looking at a dual AGN, but at a high redshift. Okay, and we started looking at this because this is one of the rare cases of a dual AGN studied by JWST. I have proposed actually twice, but we didn't get time. Now, this is the details about the source. It's a optically selected dual quasar at a redshift of 2.17. And I thought the method by which they detected this dual quasar was actually quite interesting. Because this dual quasar in earlier studies in SDSS was thought to be only one quasar. But when they looked at this quasar with Gaia, they found that it's varying with time. And so when they did HST observations, they found that it's actually two quasars. and the quasars are going around one another, and this brings about the slight wobble. Okay, so that is a program not done by us. It's called Vodka. And so they have detected these quasars, and this dual quasar system has actually been studied, and nothing just goes unnoticed by JWST. So we actually are looking at something different. We are looking at the morphology of the bulges. And so she has been doing this, and we looked at this is with HST. This is what Abhinanda has done with HST, and you can see two clear bulges. Now, this step actually is very important because there are two papers which suggest that these two quasars are just gravitationally lensed quasars because their spectra are actually very similar. And after doing this GALFIT, we have become convinced that it can't be a gravitationally lensed system. It is actually two bulges. And this is from not from our work, but their paper, where you can see here apart these two quasars. There are two bulges, but there's also a disk around it. And so one of the things that Abhinanda now is doing is to understand this disk, understand its metallicity and its different properties. And this is the, these are the wavelengths. Since we're looking at high redshift, this source is as high redshift of 2, we're actually looking at it in UV and in G band, visible. This is U band and this is V band. Yeah, this is also UV band. So that gives us a slight range. And using this study, we found that the two bulges had sizes of 2.4 and 2.9, very close. And when she did the GALFIT, she did find some emission, what shall I say, some signature of a disk, emission coming from a disk. So that was quite exciting. I think, yeah, that's the last slide I had. I'm in time, I think. No?
Yes.
Okay, so I want you all to remember that galaxy mergers will lead to the formation of two nuclei, often embedded in a single envelope. Okay, and the nuclei can have different pairs, AGN pairs, which are dual AGN, or AGN star forming pairs, or star forming pairs. Now, what we find in our study is that the dual AGN appear to be more common in evolved systems. Evolved system means like elliptical galaxies or possibly bulges of disk galaxies, more likely S0 galaxies. We also find that the supermassive black hole masses of merging galaxies, close mergers, are higher than the general population, which suggests that the black hole masses grow in the merging process and not just due to black hole coalescence. Okay. And lastly, the evolution of dual to binary supermassive black holes may involve the disruption of the stellar bulges and the formation of a stellar bridge. Okay, and such features are detected in the source which I just showed you, NGC 6240, which is our nearest dual AGN. So I'll stop here.
Okay, questions? Sorry.
Yeah, so at the very beginning, you
Huh.
were saying that sometimes if we cannot see the supermassive black hole at the center of the galaxy, we should think that it has been kicked. Has there been any confirmed cases of galaxies where the supermassive black hole is absent?
I think M32 is one such case. That's a dwarf galaxy. But yeah, I think there people have found it difficult from stellar. Yeah.
See, like I think 2 years back, there was this paper by Peter Van Dogem, and Oscar was one of the co-author in that paper. So they were talking about the kicked runaway galaxy. It was caught in action.
Mechanism for this runaway of
So there can be two supermassive black holes, an intruder coming close by, and it gives a kick. What is that method called? What's called? Yeah. The fly by, yeah, it
Yeah.
comes
Like
as
slingshot.
slingshot. Yes, yes, yes. Yeah, gravitational slingshot. So it will come and it will give it so much momentum that it will come out. Now, this actually has been found in some of the spectra of galaxies. They are called offset AGN. So the AGN emission line is not at the, I mean, you may have two AGN emission lines, but one of them is not at the, yeah, at the H alpha frequency that or wavelength that you would expect it. They're called offset AGN. So those are also another.
But observationally, there are few cases.
Hmm.
Okay, let's yes.
There was a hand there.
Observe that origins predominantly are found in evolved systems.
Yes.
So, is there a way to know that were those mergers actually like, or what was the amount of dryness or like the amount of gas that there was present, or if these galaxies had a previous history of merger or something like since they were already evolved. So, what would be like the gas content of these galaxies, and therefore we see only aging activity only in the ellipticals at the center and not poor agents in the other unevolved.
Okay. So that's a good question. I think that if we wanted to do that, and I haven't done it, you'd have to do deep observations of those with the dual AGN. Because if there has been mergers or past history of merger, you will find structures like shells, okay, within the elliptical galaxy. Or if it's a disk galaxy, you will definitely see some disturbance in the disk. Okay, you might find another spiral arm, non-axis symmetry, m is equals to 1 type spiral arm, not m is equals to 2. So your tidal perturbation, tidally disturbed galaxy. So you would have to do individual study of the sources. So we have, yes, morphological signatures, which we didn't do. We haven't done yet. There are actually many of the galaxies, and they are from SDSS, do not have deep enough images. So that becomes a problem.
Other questions? Or you can ask.
The question is, let's say two galaxies are merging.
Huh.
But the central assemblies are not acting.
Huh.
In that case, normally for a single galaxy, it is difficult for the assemblies to be active because of the process that there is no very efficient process to lose the angular. So there is a probability that the galaxies assemblies can become active.
Yes. Yes.
Probability of this thing. Compressor to be active.
Okay, okay. So what is the probability that they'll be both active in a elliptical merger then? Yeah.
Because as they're merging, the gas supply can be.
Oh, but if it's elliptical, there won't be no gas supply. If it's elliptical, there'll be no gas supply because ellipticals don't have gas. But even then, if it is this disk, you will find definitely that, yeah, very big chance. Because in disk galaxies, it's very common for the gas, even with small gravitational perturbations, for the gas to lose angular momentum, some of it, and fall into the center. Now, it falls into the center. Center is only 1 kiloparsec radius. There, the gas piles up, and gas surface density increases, and star formation or starburst happens. So there, the probability is very high. But if they are elliptical mergers, then the probability can be a little lower.
Yeah. So what is that's a very important and very obvious question. So actually, what Professor Das said is, if it's evolved galaxy, that's gas trip. But if you look at all these, Hawking's paradigm and everything, and when you see that, over the time, so for example, in the early part of the universe, like redshift 2, 3, you have major AGN activity being fueled through merger events. So major mergers are actually fueling AGN activity. And because there is this belief that AGNs go, and then there is feedback, and then they go down and they go
Cycle,
back. So
yeah.
there's a lot of it, frequent mergers. In simulations, it's very much seen that AGN activity is triggered by major merger events, and also there are observational evidences. Because if you look at the merger rate over redshift, merger rate, and if you look at star formation and AGN activity, there are correlations.
Other questions?
Yeah.
About your detection of AGN in HDH, you confirm them as AGN only by the BPT diagram or by spectra as well?
So it's the same thing. So to put them on the BPT plot, you have to extract their line fluxes, and we didn't do it. We took the line fluxes given by SDSS, and we took their ratio H alpha to N2, and I think we took.
So since I already have the spectra, so I already know whether they are galaxy or AGN. Right. Without doing that.
No, I mean, see that was a problem for us, because when we got all this result from Gothic survey, then I went to look at the SDSS classification, and out of 682, SDSS had classified only maybe 50. So we had to do our own classification by taking all the fluxes that is listed in SDS.
Since we have spectra, so I know the redshift and I know their position. Without looking even at the image, I can see how close they are. And
we know how, from redshift, you know how close they are.
Then I don't need to go for this image processing to find out whether they're nuclei or not.
I have to find them now. Without image processing, how do we find them? Yeah. They're not identified in it. We found them. Yeah. So, Anwish.
I'm not saying this is organic. I'm saying I know the position of the source. I know its redshift. So I can just
matching redshift and
I don't have to do image processing. That's what I mean.
No, without image processing, you can't find the pairs.
Finding the position of the nuclear or something like that.
What he is saying is that if we have the spectra of the sources, then we know the redshift of the sources. We know the array deck of those sources. In that kind of matching, we can tell that they are systems or not.
So I guess you could but you could do it that way. So for you, what you're saying is we download the list of galaxies. SDSS had defined the galaxies. We find their RA deck. We find their redshift pairs. Okay. But yeah.
Spectrum.
Yes.
It will be just a combination of two galaxy spectrum. You cannot really tell anything from that.
No. I am taking only the redshift. That already they are taking the same information to see whether they are close by or not.
Yes.
Pairs that you selected got in the search. What those all identified objects in SDSS?
Yes, because they all form part of that 1 million. Okay. They were all cataloged. Yeah. No, we did do. So what happens is, we took that 1 million, we downloaded, and then we looked at the images. Now, some cases, SDSS has identified galaxies, but there's nothing there. In some cases, it mistakes galaxies for, say, some error in the image. So if you go by just what SDSS says, you will not be able to get a sample of 2 AGN. Yeah, you could. Yeah. Yeah. Yes.
See that what is the contact.
Also, the possibility of an AGN is a compact source, right? We are looking for compact nuclei. We don't just want any galaxy. We don't want just any galaxy pair. So that's another reason why we did the visual image processing.
Other question? Already?
What kind of spectrum or acidity do we expect from this marking galaxy? Will there be how much different? Like if there are two
Hmm.
the fluxes from those axes this should be different from
Hmm.
axis.
Hmm. So yeah, I understand what you mean. If you have the dual AGN, is it very different from a normal, just an isolated AGN? It's actually not that different. It only becomes different if the AGN become very close. Because like that Markadian 212 that I showed, there the AGN are separated by 10 or 11 kiloparsec. Okay, but yeah, here. Okay. So you see here, they're separated by 10. Actually, the AGN were not very different. One was Seifert, I think, one was Liner. Okay, but if they come very close, if you look at this AGN, see, this is a Seifert nucleus. This is also Seifert. So here they are quite strong. So that's because they are very close. So I think when they become very close, this is what we have studied. But you have a very valid question. It's a very important question that when they come very close, how are their spectra different? Yeah. It's an interesting question, actually. No? Ah, ah. Hmm. NLR will be affected. BLR, I think, is like close to close.
1%. If we come less than a parsec, then maybe the BLR will be.
That can also happen in this spectrum, right?
From those
The
ALR spectrums can understand about if they are dual AGNs or not.
Just from the BLR spectrum. NLR spectrum. Yes. So the NLR spectrum is one of the ways in which you detect 2 AGN. Because the BLR is very close to the black hole. NLR is far away. Okay. So if you have 2 AGN, then NLRs are more likely to get affected rather than the BLRs. Also,
so the split lines that you are seeing, from which you began the whole thing, those are what? Those are NLR lines or?
NLR, yes. Because mostly you have to find them in O3. O3 emission comes mainly from NLR. So yes, it is coming from the outer parts. And also another thing about BLR is, BLR emission is very broad, right? And when I was looking at the KISAR sample long ago, I found that those Seiferts, which are very broad, Seifert 1, you can't distinguish if there is, then you're trying to find 2 peaks and very difficult.
So I have a general question about this, how many double sort of binary mergers are very common. Maybe not in the local universe, but relatively high redshift. So ideally, you should find many dual agents, even many binary agents.
Yeah.
But I think about last 20 years, people are doing various kinds of studies to find them, but only very few of them have been found.
Yes.
So is it a completely observational thing, or why can't we find more?
More, yeah. So this is a question also a referee asked, and because when we went through the numbers, I think this final sample that we got, we have found only some 1 to 2% are dual AGN. Okay, so and I remember thinking about it. I think one is the life cycle of the AGN. One is that also our observational capabilities. Because once they become very close, we can't find them. Another thing is that sometimes, if they're not giving out AGN emission lines, we can't detect them.
Yeah, so out of all the mergers, but also there is a thing where, this whole Phil Hopkins, etc. picture is that all mergers will eventually lead to
more bigger galaxies.
Bigger galaxy, but also AGN.
Yes.
Ah.
There will be an AGN phase after the merger phase.
Ha.
In between, there could be a sort of a large of this infrared,
Yeah.
infrared galaxy.
Yeah.
So then all mergers have a corresponding AGN phase. And so then that and there could be dual AGNs in them. Then we may or may not detect that.
The dual AGN has to simultaneously shine. I mean,
Yeah, they have to.
couple of things. Right. I mean, for example, there could have been a small phase where they were shining and we couldn't catch them in that phase.
Yeah, AGN cycle is one reason.
That whole merger background, because all of us expect that
Yeah.
supermassive black holes have to merge.
Yeah.
Now,
Yeah.
many of them will shine as AGN.
Yeah.
How many of them
Ah.
catch?
Yeah. I've also wondered, I mean, I haven't checked the literature for this, but when the AGN are coming closer and closer, at some point, do their accretion disks merge? Do they get stripped?
Yes.
Okay. Yeah. So when and if then they become silent to us, we can't detect them.
Yeah, for example, UJ287, there it is assumed that one black hole is going through the accretion disk of the other black hole, and there is a periodic sort of change in the emission.
No.
That gives a periodicity to their light.
Yeah.
That's the
That's the light.
So then their accretion disk obviously interact.
Yes.
But since there is a 1:100 ratio or something, so the big accretion disk is not completely disrupted. It just causes some change in their emission.
Yes. Yeah. But the small one in the models is not assumed to have an accretion disk, is it? I think it's only the big one that has.
Also, there is obscuration. That's another.
X-ray search.
Once there is a merger effect, there is so much dust and everything there.
Yeah. Yeah, that's why there are a lot of infrared searches for these binaries. Yeah, dual systems.
Because if the nanograph result is right, then there is a lot of, I mean, that comes from some number of
Yes. But the numbers we detect in the local universe is much lower than what is predicted from, say. But then nanograph is like accumulation of all, right? Because you are not confined to any redshift, na? Yeah. So I don't know if anyone has done that, put it all together that.
People who do, I don't know about supermassive. Well, we had a conference in ICTS like 6-7 years back where the GW people were actually asking the AGN community or cosmological simulation would give them clues about what could be the supermassive black hole merging population,
right? Yeah.
Cosmology can't simulate black holes less than
exactly. Yeah. I feel that also that there are many wandering black holes, in galaxies, and these can also give rise to, I'm not sure if it will give nanograph type wavelengths, but they will also contribute. Also, when the two black holes come closer and closer, there are a lot of stellar systems also that are, like, for example, this bridge that is forming, right? So there also, I feel that there a lot of gravitational wave origin can also be there, because when the systems are coming so close to one another, there will be density of black holes will go up.
Okay. If there are no other questions, let's hang up the document.
Oh, আমার না honorarium লাগবে না, honorarium আমার কলেজ তো সই করতে হবে কিছু? থাক। না 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 না